All right, so let's begin section 1.8. 1.8 continues on with proofs, introducing more strategies and more ideas related to proofs. So let's begin with how do you disprove something? Well, disproving something is the same as proving its negation. So to disprove some statement, P, what you do is you prove not P. That's all. You just prove the opposite. Let's see. If we make a claim, let's look at this claim. The claim is for all n in Z. So for all integers n is less than or equal to n cubed. Is that true? Well, 1 cubed is 1, so that would be the equals. 2 cubed is 8. The cube is bigger than 2, right? So 3 cubed is 27. Well, it got bigger when you cubed it. So like it seems to be true, but in fact, it's not actually true. Let's show that this is false. So to show that this is false, here's what we need to do. We need to look at the negation of the claim. So I just want to say here, this is false. We're gonna prove that it's false. Let's look at its negation. The negation, I'm just gonna write a negation in front of it to begin with. Okay, so now the way you negate that is that you use De Morgan's law, right? Instead of for all, this is going to become there exists an n in the set of integers, not for all n, but there exists an n. And then what we need to do is do the negation of what's inside here, right? So the negation of n is less than or equal to n cubed would be n is greater than n cubed. Okay, so now what we want to do is prove this. As you can see, when we negated the for all, it became a there exists, right? So to prove the existence of an element that satisfies something, all you need to do is find one. You need to exhibit one example of an n that is bigger than its cube. That's all. So let's see if we can find one. Let's think, well, we already tried 1 cubed is 1, right? That worked. 2 cubed was 8. That's not going to do. Let's try going the other direction. 0 cubed is 0. Well, that's still equal, right? But what's negative 1 cubed? It's negative 1. That's also still equal. What's negative 2 cubed? Aha, it's negative 8. That's going to work. We'll prove it by saying, here, proof. For our proof, we'll say let n equal negative 2. Negative 2 cubed is negative 8. And negative 2 is greater than negative 8. There we go. Negative 2 is greater than negative 8, right? So this disproves the claim. We did it. This is basically disproving a universally quantified statement, disproving a for all by finding a counterexample. What we found here, this is called a counterexample. And you only need one counterexample to disprove something which is claimed for all. So on the flip side, if you make a claim about the existence of something, then we have to approach it a little differently. Let's claim that there exists a number n, again an integer, so we're using the domain of integers, such that 2n equals 5. Okay, again, this is false. No such n exists, so let's disprove it. We'll find the negation of this claim. If you negate there exists n such that 2n equals 5, that's equivalent to saying for all integers n, 2n is not equal to 5. Negating this equals gives us a not equals. So can I prove that? Let's see. I might need a little more space for that. No, maybe not. Let's see. This seems kind of hard to do. This seems kind of hard to do, actually. Think about this. If I want to prove that for all integers n, 2n is not equal to 5, how am I going to do that without just plugging in integers forever and then showing 2 times 0 is not 5? Okay, 2 times 1 is not 5. Okay, 2 times 3 is not 5. Okay, I can't do that forever. I mean, there's an infinite number of integers. That's literally impossible to prove using that strategy, right? This is what I mean about, given an infinite amount of evidence, you can never really prove something is going to happen for all. Like, if the sun rises every day, that still doesn't strictly prove that it's going to rise tomorrow, right? If 2 times an integer is never equal to 5, well, you can't ever prove that it's never going to be equal to 5 because you have an infinite number of integers to work through. So instead of proving this negation directly, what we can do is actually prove it by contradiction. And so interestingly, to prove something by contradiction, you assume it's negation, and the negation of the negation takes us back to the original claim that we started with. Right, so actually we want to disprove this claim by supposing that it is true, and then finding a contradiction that follows from that. So let's go like this. We're going to assume, seeking a contradiction, that there exists an n in Z such that 2n equals 5. Okay, well then, n must be 5 divided by 2. But 5 divided by 2 is not an integer. Thus, n is not an integer. Well, that's interesting. We said, assume there exists an n which is in the domain of integers that satisfies this, and then we're able to conclude that that n is actually not in the domain of integers. Well, that is a contradiction if I've ever seen one. You assume it's an integer, and you show that it's not an integer. So therefore, we could write there doesn't exist, and one way to write this symbolically is you could write there doesn't exist an n in Z such that 2n equals 5. Okay, that's the same as saying the negation of there exists, but there doesn't exist an integer that satisfies this. So that's how that's one strategy by which you can disprove a claim of existence. You can suppose that it is true and then prove by contradiction that it must be false.